about real science.
Now we're going to talk about how we generate electricity regardless of what type of power plant you're going to use. And this, with the exception of solar. Solar uses the photoelectric effect, which is one of the things that Einstein figured out. You might have heard of him. And also Einstein figured out why electromagnetism really happens, right? Like from a real physics standpoint, from the nitty-gritty standpoint. So what we talked about yesterday, ignore this for now. This is where we left off. If I have a loop of wire and I have a magnetic field, which I've drawn a little more better today, which is coming out of the board, and so this loop of wire is within a magnetic field, and so I have this external magnetic field, and it's the rate of change of that magnetic field, dB dt, is positive, meaning it's just increasing in strength coming out of the board. So it's like I'm bringing the north pole of a magnet from behind the board and moving it towards you guys, right? Then I get an induced voltage, which will then drive an induced current, right? And that's what we see. That's what we see in all the examples. And so what happens is that the current gets induced such that the magnetic field that it creates fights the changing magnetic field. Nature doesn't like change, and so if I have an increasing magnetic field this way, then the induced current is going to create a magnetic field opposing it, right? It's going to try to oppose it. And so as this field, and remember, if it's a constant field, nothing happens. We showed that yesterday, right? They wondered, okay, I know electricity creates magnetic fields. Can magnetic field create electricity? Not just by itself. It has to be changing. You have to have a changing magnetic. And magnetic field doesn't necessarily need to be changing. What needs to be changing is the magnetic flux. That little battery-powered motor that Mr. Science Asylum made, the magnetic field coming from that magnet wasn't changing. It was constant. What was changing was the magnetic flux through the loop, the amount of that field that was actually passing through the loop. So anyway, I have an increasing magnetic field this way. So Bradley, which direction is the induced magnetic field? Into the board. So I'll put that one in purple. So I get an induced magnetic field into the board.
Why does it feel like I start to understand so much more at the end of the
That's typically how it happens. If you're like me in college, then you start understanding the previous unit when you're like almost to the end of the next one. That's my college life. At least after I transferred to Cal. Yeah, it was brutal. Anyway, so I got that induced magnetic field, and then we just use the right-hand rule to say, all right, which direction is the current going to be going?
Clockwise.
It's going to be going clockwise. And so I'm going to have current through the loop clockwise.
And that's induced current, right?
That's my induced current. I end. Here. All right. And then if I was to say and notice this is where this negative comes in. Usually we deal with this negative here just by kind of conceptually braining our way through it, right? We just kind of think about, all right, magnetic field is pointing that way, but it's decreasing. So I need the induced magnetic field is actually in the same direction, right? And so it's going to create, and so you use the right-hand rule and just your noggin to figure out what direction the induced field and the induced current are going to be. Technically, though, if I've defined a standard coordinate system, here, a current clockwise would technically be negative, right? We usually talk about that direction as being the negative, clockwise as being the negative direction, and I have dB dt being positive, right? If dB dt was negative, meaning that field was shrinking, then I would end up with a positive current, right, in our standard coordinate systems. But just understand that negative, usually in practice when we're doing the equations and we're solving the problems, you just kind of ignore the negative and talk about the magnitudes. And then if it asks for directions, then you just use our logic, what we just did, and then use the right-hand rule to tell what direction the induced field is, what direction the induced current is going to be. Okay? Make sense? All right, so let me show you a couple examples real quick. Everyone say hi, Caesar.
Hi, Caesar.
Hi, Caesar.
Everyone said hi, Caesar.
Goodbye, Caesar.
Caesar says he doesn't want to talk to you guys. Oh, Caesar said hi, Caesar. All right. Okay, so I did try it this morning with my little simple motor setup with the coils of wire and just the magnet, the simple way. And I was getting little tiny spikes here that I could see, but you guys wouldn't be able to see. So what I did, I took this electric motor, and instead of hooking up the power source, and I can hook up the power source just to remind you how this thing works. Oh, I did the wrong thing. So there's our electric motor. So that's using the power supply. But now, I disconnect the power supply and hook my motor up to the galvanometer. And when I twist the thing,
You can do it even faster.
okay, you can't really, can you, okay, that's,
One of those, compressed air fans.
okay, it is, if I could spin this faster, you would see the needle move. It's not really moving. It's moving a little bit. For some reason, that was working better earlier today. Let's do something that'll be a little more obvious. And that's this little tiny motor. Now, what he said, back in the day, they were able to do this. They weren't able to get much work out of it. They weren't able to actually get a lot of mechanical energy out of this stuff. They were just noticing the effects of doing cool experiments. Our technology has advanced so much that we can get a huge amount of that comparatively to like what they were doing in the 1800s. We can get a huge amount of electricity out of something like this. But I'll show you its motor out. This is just a tiny electric motor. Would be used for like a drone propeller or something.
Oh, it sounds exactly like.
Or a dentist drill or something.
It sounds exactly like those cheap drones that you would get as a kid that you like try to fly.
That you break in like 10 minutes.
Yeah.
Yeah.
Maybe you get yelled at.
So, but whenever I turn this motor into a generator, and I'm just going to spin this little post with my fingers and watch the needle. Can you guys see the needle?
No.
A little bit.
I'll try to get to where you can see it. Oh my gosh. Why are all my demonstrations just not working? Bradley,
Bradley's fault.
you're like right in front of people. Move, let them see.
Oh, I can see the wiggle. I can see the wiggle.
This was working a lot better this morning. Maybe it's the galvanometer.
That's what I was saying yesterday. Put the wires real fast.
No, it was moving, so it wasn't that the wire was different.
Is it turned on?
Turn it on, turn it back on. Turn it off, turn it back on.
That's a lot of galvanometers.
No, these aren't all galvanometers. Oh, I have it up here.
Just use beams. What can be used for anything?
Wait, they're not here. Where did I put them? Oh my gosh.
In the future, whenever you do the manual labor moving that motor, you should get like a compressed air tank or something.
Yeah.
Oh, cookies.
Use a motor and spin the motor.
Yeah, it's actually not the electric motor. Oh, I'm stupid. I'm insane.
Think all of this.
Welcome to the club.
Anyone who willingly takes this class,
I wouldn't say stupid.
just yeah.
Glutton for punishment.
This class
Mentally incapable.
There we go.
Oh,
There.
yeah, it was definitely the
So at home, I just got this little tiny motor, and instead of hooking it up to the power supply, I hook it up to the current detector, and then I just spin the post, and I generate electric current. Okay. Now again, that can't happen without the wires wanting to generate their own magnetic field, right? So the wires within the motor, within the generator in this case, end up generating their own magnetic field, which leads me to another cool demonstration. Sorry, it's slanted there at home. So this is a ring thrower or ring launcher. I'm going to get... Well, first of all, there's a coil of wire that is going to get a large alternating current generated within it. So it's going to constantly redirect the electric current direction in the coiled wire back and forth. Got a big piece of iron here that I just put in there to magnify the magnetic fields. And notice there's a plastic cover here, so when I slide this light bulb with a couple coils of wire connected to it over the top, and I run electricity through the inner coil, then through electromagnetic induction, electric current will be generated in the outer coil that's attached to the light bulb in order to try and oppose the magnetic field generated by the current on the inner coil, right? And so what ends up happening is that you actually get a magnetic force here that I'll show you in a second. But here, instead of using that magnetic force or the magnetic energy to maybe, say, launch something into the air, I'm just going to use that energy to light the light bulb.
Jesus Christ.
Notice it only lets me go for like less than a second because, it's a lot of juice. Right. If instead...
There's more energy being generated, or more energy being used in the...
Probably, yeah. So here I have a piece of aluminum ring. It's an aluminum ring. So the same thing's going to happen here. When electricity gets generated in the coil, then it's going to generate a magnetic field. And then this ring is going to feel that magnetic flux through its center. And because the current is alternating, it's going to keep changing, right? And so there's going to be an induced magnetic field due to the induced current within this ring. And that magnetic field is going to oppose the direction of the changing magnetic field here. So we should actually get a magnetic repulsion between the two, right? So I'll point it this way.
Launch it into the cabinet.
Thank you.
That's loud.
Yeah, so
That's a weapon.
yeah. Now what's cool is I'm getting showered with dust from the ceiling. Does anyone want to volunteer?
Oh no.
Come hold on to it and try to fight it being launched.
Logan, did you see
I have
Logan fly
for
up?
2 weeks.
We just see Logan fly
Wanna
up
get
into
shot?
the ceiling.
Yeah.
Hey, move, Logan.
What do you feel?
It's hot.
Do it one more time.
Yeah, hot.
Now it's like pretty hot, right? Now it's like almost burning hot.
Now it's like Connor.
So notice with the light bulb, the energy was used to light the light bulb. With the ring, first, the energy was used to give it kinetic energy. When you prevent the kinetic energy from being gained by it, because it didn't increase its temperature then, well, the current that's going through it was then, the energy of that current was just used to heat it up. So it got noticeably warmer, a lot warmer.
Is that
Imagine
how electric
if we
welding
were
works?
conductors.
What's that?
Is that how electric welding works?
I'm not really sure.
Okay.
So if I get a piece of plastic, what do you think's gonna happen?
It's just gonna get really hot.
Oh, there's no current generated in a piece of plastic.
Oh yeah.
It's an insulator, so you can't get electric current generated within the plastic.
What if you put a piece of plastic in between the metal?
What if I did this? That's metal. Oh!
What if you accidentally got them switched and you put your head in?
Oh, it's
You see that?
There's a little space.
There's a little gap there. So usually, well, many times I would then point it at you guys. But yeah, there's a gap there, so you can't get a current. You have to have a closed loop current, right?
What
In
if
order
you
for
have
this to
a
happen.
piece of plastic?
Have you ever made the mistake and actually
No, no.
I
Okay.
think he'd still be teaching.
All right, so making sense conceptually, at least.
It's making magnetic fields.
Oh my gosh, magnetic beans. Those are the best kind. Best kind. All right.
My beans are sticking together. I can't get the spoon out. It's stuck.
So, again, now if it's a south pole, some people get a little confused if it's like the south pole of the magnet. Say we got a south pole of the magnet coming in this way. Well, the induced magnetic field is going to be such that it wants to keep that magnetic field the same. So if a south magnetic field is coming this way, you would end up getting it, and it's increasing. Say the south pole is coming this way and it's increasing in strength. Then you would probably expect that the current would have to be in the other direction, which means that the north pole, when we draw our induced field, it's always like in the direction of the induced north pole, right? It's not an actual magnet, but it's in the direction of the induced north pole. So if the south pole was pointing this way, if I was moving a south pole in, then the increasing magnetic field that's coming this way is actually negative, right? Because it's going from the south pole to the north pole. And so the induced north pole would be in the same direction. Because if you get a north pole and a south pole in the same direction, they end up negating each other, right? And so, but always think that when you're doing the induced field, always think in terms of the north, like you're thinking the direction that the north magnetic field would be pointing, okay? Even though there's no actual magnet
Did
there.
they ever ask a question doing it with the South Pole?
I don't see it nearly as often, but yes, definitely can. Just know that you're trying to keep the field the same, right? What has to happen to keep the field the same? And then after you just establish that, what direction must the induced current be in order to create that induced field?
The opposite of the
Yeah. Okay. So notice that Faraday's law, this is part of Faraday's law. We're talking about an induced voltage. Like I mentioned yesterday, though, right at the end, that voltage I can't draw anywhere within the loop, right? If it's a battery powering a circuit, then I get this symbol for the battery, right? And then I have the loop. This is my EMF or my voltage source.
That's a lot of
Okay.
heat.
What's that?
That's a lot of heat.
It's a lot of heat. Yes, that's a short circuit. So, but I can pinpoint my source, my voltage source. In this case, the voltage source is within the entire wire. Okay, it's within the entire wire. Entire wire. And so I've drawn this as just a little segment of the wire. I have the induced current I know is there, right? Because I saw the light bulb light up over there. I've detected it with my little galvanometer. I know the current exists within that wire. Well, if there's a current, charge must be flowing, right? That's literally what electric current is. If charge is flowing, there must be an electric force pushing that charge. And if there's an electric force, there must be an electric field within that wire. There must be. And yes, our conventional current is not the real direction that the electricity is flowing. However, the mathematics assume that it is so. So we have, if the induced current direction is this way, so must the electric field direction. Okay. Again, we can't draw like the voltage in this loop of wire like a capacitor or a battery. We can't draw the voltage source that way. So it's a little more complex. To kind of illustrate what we're going to do, though, I've got a capacitor here. I'm just going to remind you of something. I want to know the potential difference. As I integrate from A to B, it's the integral of E dot dr. Remember doing all that? E dot dr. Negative, sorry, it's the negative. Why is it negative? Because I end at the negative and I started at the positive. The voltage here is smaller than the voltage here. So if I calculate a potential difference, the result must be negative, right? So that's where the negative comes from. So it's negative. The electric field between capacitor plates is constant. When I integrate over all the drs, the little tiny infinitesimal drs, then I get a total distance d. And so the potential difference is just negative electric field times capacitor spacing, right? We use the same general idea here to determine an expression for, or an alternate version of the expression for the induced voltage, right? We just take this entire wire, which has, we assume to be a constant electric field if the current is the same in all parts of the wire, and we just do the same integral. But because we don't have a final point that's at a lower potential than the initial point, we just write it as our induced EMF, which is the same as this induced EMF, is going to be, and it's going to be positive now. We don't put the negative here because, again, we're not doing final minus initial. We're not having an actual change in the electric potential per se. We get an induced voltage throughout the whole thing, and so we just integrate E dot dr, but because we are now going around a loop of wire that has certain length, generally the induced voltage is written in terms of not dr, but dl. Right? So we integrate the electric field dotted with dl to get an expression for the induced voltage. But it's essentially the same thing as our definition of electric potential difference, the negative integral of E dot dr. But we just can assume it to be positive, and it is ubiquitous throughout the entire wire, and we just integrate E dot dl. And that gives us another expression for our induced EMF, which gives us the final version of Faraday's law for what we're doing. Again, mathematically formulated by some guy not named Heaviside, because, screw that guy. So we get the expression EMF, this is how it's written on your formula sheet. The EMF generated via electromagnetic induction is equal to the closed loop integral. Should have written that, sorry. Now that we're integrating over the entire loop, you have to have the closed loop, right? And you have to integrate over the entire closed loop. E dot dl. But as we showed yesterday, or demonstrated yesterday, it's also equal to the negative time rate of change of magnetic flux. So that's how it is on the formula sheet. Realize that d phi dB, bad blue, is the same thing as d dt, the time rate of change of the integral over the open surface, where the open surface is literally this area here, right? The open surface that's bounded by the wire, I actually wrote that, bounded by the closed loop of wire, B dot dA, which is very similar to the expression we use for magnetic flux. Only magnetic flux, again, was through a two-dimensional surface within three-dimensional space.
You mean electric flux?
Electric, that's what I said, electric flux. Yeah. You calling me a liar?
Yeah.
Oh, okay. All right. That making sense?
Making beans.
Making beans? That's Faraday's law. That's our fourth Maxwell equation. That's all you need. I told you about that guy, right? Like my first day of college level, meaning junior/senior level electromagnetism, the teacher held up the textbook and he's like, difference between you and me? You guys need this whole book. I just need the 4 equations. Literally do everything. Yeah, anyway. Any questions about that? You want to do some examples maybe?
Yeah.
You didn't tell me to smile. All right.
I think the day after the AP test, we should have a BYOB day. Bring your own beans.
Bring your own magnetic field.
All right.
It's going to induce a magnetic field on the room.
Now, if you watch the Dan Fullerton video, you'll see. I think when I wrote these, it's the same example that Dan Fullerton does in his video. So keep that in mind. But it's very illustrative of some of the pitfalls that people fall into when they try to use Faraday's law. Faraday's law looks complicated. It can handle some pretty complicated situations, but if you understand what you're doing, it's really not that bad. So let's say I have a circular loop of wire that has a light bulb on it. I'm just going to draw it as a resistor, though. As a resistor, R. And I have a magnetic field that is pointing towards y'all. So I have a magnetic field. This is an external magnetic field that is going through that surface. And now you might think, when would you actually see this? When would you actually see a magnetic field as a function of time that would be equal to something like 3t squared minus 2t plus 1? Like when you actually wouldn't. However, when you actually have a generator with the rotor spinning and it has the large bar magnets that are actually causing the electric current to have, there are functions associated with those. It's just those functions are way more complicated than this one. So this is where we start. We start with a simplistic situation like this that's not very practical, but then you use the same ideas for the more difficult, more practical solutions that you need to do when you're designing electrical generators.
Would those be sinusoidal because it would be?
Oh, yeah.
Okay.
And like Tim pointed out yesterday, you remember that, Logan, right? You weren't
Yeah.
you weren't out losing a tennis tournament or anything, right?
Oh.
Timothy pointed out that, like, yeah, because how they're configured is what generates the alternating current that we use,
Okay.
which is much more efficient as far as transport than it would be if we were just to direct a continuous direct current. Okay, so we have a magnetic field going through this loop of wire, and that magnetic field varies as a function of time according to that equation. And our resistor is 100 ohms. Okay. And number A says find the induced EMF as a function of time. Meaning we want to find an equation for the induced EMF. Okay. Generally, let me write Faraday's law again. Generally, we use, to find an EMF, we use this one. Obviously, here that's going to be the case because we have a magnetic field function, right? So when we use it, we're generally using that. Sometimes when we use the Faraday's version of, really the Heaviside version of Kirchhoff's voltage law, which we'll talk about next week, then we'll say this is equal to that, but we're actually usually going to evaluate the right-hand side, the most right side. Are you live there, Jen? Okay. And so to figure out that, we're going to use, there's three terms there, right? All equal to each other, so you just pick two of them. So to figure out what this is, I'm just going to use, that's the negative derivative of the magnetic flux with respect to time, where I know that the derivative of the magnetic flux, and remember, in practicality, I'm going to drop the negative, right? And I'll be able to, and a later part of this problem will ask about the direction, but I'll use the right-hand rule when I get there. So I'm just going to talk about the magnitude of the EMF. It's going to be the derivative with respect to time of the magnetic flux, which is the integral of B dot dA, that integral over that open surface. You don't have to write open surface all the time, but you do want to understand that it is the magnetic flux through this open surface that's bound by the wire, by the circuit itself. Okay. This is where students get, because you got the derivative of an integral, right? And students kind of freak out about that.
Second FTC.
What's that?
Second FTC.
Yeah, I forgot about all that stuff. But the thing here is that I'm integrating with respect to the area. And then I'm differentiating that with respect to time. So you kind of handle them separately, right? I want to get an expression for the flux. That's why I want the derivative with respect to time of the flux. So I use the integral of B dot dA to determine an expression for the magnetic flux, and then I take the time derivative of that. Does that make sense? So I just leave the ddt there for now, and then I figure out what B dot dA is. Well, I'm going to define my area vector as coming out of the board so that it's in the same direction as the magnetic field. Remember, the area vector is always perpendicular to the surface, and so I've got this flat surface. Area vector comes out this way. So I'm going to be, B dot dA, sorry. That's on your formula sheet. B dot dA is going to be B dA cosine theta. Cosine theta is 1, so it's going to be B times dA. B now, though, so now it's going to be the integral of B dot dA. I already wrote that. B dA. Now, this is where some students say, well, I can't get the magnetic field out. I can't bring it out of the integral because it's varying.
Plug it in.
It's wrong. Well, yeah, that's what you're going to do. The magnetic field varies with time. Here, we just need an expression for the magnetic field or the magnetic flux in terms of the area and the magnetic field itself. And then we differentiate it with respect to time. This integral is with respect to the area, right? It's with respect to the actual surface area of this guy. And so it is constant because I'm not talking about it varying with time right now. I'm talking about the magnetic flux through that loop. And whenever I do that integral, I end up with a function that is a function of time, and it will vary, so I can take the derivative of it.
So you can take the d out, and then it would be
Yeah.
d over dt.
Well, it's going to be the derivative with respect to time of, and what happens whenever I integrate dA here?
You just get the area.
You get the area, and I should have the radius here labeled. I'll use lowercase r because I got a capital R for the resistor. So it's going to be the derivative with respect to time of my magnetic field, which is 3t squared minus 2t plus 1 times the area, which is pi r squared, which is constant, right? I'm doing this right, aren't I? Yeah.
I hope so.
It's just area, right? And so that's going to be pi r squared times the derivative of this, which is 6t minus 2. Right? And so that is my induced EMF as a function of time. Right? So I could write it epsilon as a function of time equals that.
Wow.
So again, when you do integral of b dot dA, don't worry about the time. Don't worry about it varying. You need an expression for the magnetic flux as a function of time, but then you do the derivative afterwards. B is not constant with respect to time, but it is constant with respect to the area. Okay. And if it changes, well, then that's taken care of whenever you apply the derivative with respect to time.
So basically, the B dot dA is like how much of the electric field is going through, and then the
Literally what flux is, yeah.
yeah, and the B as a function of time is how strong it is.
Yeah. Yes, perfect. This tells you how the strength of the magnetic field varies, right?
But the amount of it that goes through just stays the same through.
At a snapshot in time, yes, you have a constant magnetic flux at a snapshot in time, but then that flux will change, and that's when you do the derivative of that function,
Got you.
and then that tells you how the flux is changing. Yeah.
It's supposed to be negative.
What?
It's not supposed to be negative.
We're just dealing with we just dropped the negative. Talk about the magnitude. Yeah. We'll talk more about that. Here, I got 2 more parts. Let's try to get them done before the end of the period. All right. This quest assignment is up. I recommend you try to take a look at it over the weekend, because we're going to be moving fast next week, because I want to finish by the end of next week.
By the way, I'm not gonna be here tomorrow or the next day.
Okay. I think I'm taking those days off too.
Ah, damn.
I don't get to.
I get to come up here tomorrow.
Oh yeah. Oh, mock exams. Do you guys have them next weekend?
Wrong weekend, I think.
Prom on Saturday.
Yeah.
So we should do the mock exam super early on Sunday then.
Well, no, because you have to stay at 5.
I'm just kidding.
I would be okay on Sunday for my
When does project celebration end?
That's Saturday night into Sunday morning.
You guys doing that?
Yeah.
Party animals.
I raised all the money, and they help too.
Huh?
My mom and I raised all the money, and they help too.
Oh wow.
Some.
Should try to put that energy into your tennis game a little more.
Yeah, we're sucking it up.
Have a good weekend if you want to.